Yeah, we need to talk about derivatives of exponential functions. Now, what separates an exponential function from just a regular polynomial function? Well, it's because of the x being in the exponent, like 2 to the x. Instead of our function being x squared, where the variable is the base, in an exponential function, the variable is the exponent. So, in general, it's f of x equals, they would use a for the base, a to the x. A is going to be a positive number. And again, just kind of for some more review here, if I have, if you look at the graph of this, 2 to the x, a to the x, where a is a positive number bigger than 1, this is what you got, what it looks like. You graph that. And again, just for some notational reminder here, we haven't reviewed the limit stuff here. If I say to you, what's the limit as x approaches infinity of my f of x? What do you got there? That's infinity, yeah. As x goes to infinity, so does the function. Now, if you go the limit as x approaches negative infinity, well, that's a little different story because it does level off out here at 0. Yeah. As you go out to negative infinity, x does, the function values go closer to 0. And so that's just verified pretty easily there by your graph. You can see that. Okay. Well, there's different things. I mean, if you do your base is bigger than 1, you know, if you turn that around and make it between 0 and 1, things change around. But we could spend a lot of time. But the main thing here is that we want to do a little differentiation. Differentiate a exponential function. That's what we want to do. Well, we usually start when we talk about derivatives. We usually start with the definition of derivatives. So let's do that. Let's talk about the derivative of 2 to the x. Well, let's just do it in general. F of x equals a to the x so f prime of x then, by definition of derivative, would be f of x plus h minus f of x over h. Limit as h goes to 0. Forgot that part. Okay? A little bit rusty. Okay. All right. Well, none of our little tricks are of much use here. Here's what we got. All right, so what is f of x plus h? Well, we plug in x plus h for x. We have a x plus h is what f of x plus h would be. Would you agree? F of x then would just be minus a to the x. That's over h. Well, the one thing we can do with this, is this right here. This is kind of the reverse of the exponential rule. When I have, x squared times x to the third, I add those exponents. Well, I'm going to go, and so I would get x to the fifth. I'm going to go the opposite here. This is the plus, so can I break it up? I can break that up. All right, so this is going to be the limit as h approaches 0. And that's going to be a to the x times a to the h. With me? And then we have minus a to the x over h. Well, what do you see there I can do? I got a common factor of a to the x. So I can pull out an a to the x. Okay? Well, if you'll notice and remember things about limits, the h is what's varying, right? I'm letting h go to 0. This doesn't have an h in it. So I can just basically pull that out, right? Because it's not at all dependent on h. So it's a to the x times the limit as h approaches 0 of a to the h minus 1 over h. Which gets me stuck, okay? I'm stuck there a little bit. But here's what we can say. What was I doing? I was doing the derivative of a to the x. Well, look at this. The derivative turns out you have a to the x in your derivative. So part of the derivative of a to the x is a to the x. Nothing changed. Now this, there's a little bit to that. Here's one example. For example, like if I did f of x equals 2 to the x, well, the derivative by those calculations there, wouldn't the derivative be the limit, it'd be 2 to the x times the limit as h approaches 0 of 2 to the h minus 1 over h. That's something, but it's 2 to the x times that. Okay? All right. Well, actually, one of the things we could do here is look at a table. And if you look at a table of values for this limit, if you punch in, put it in your calculator where you could look at it, let h approach 0, 0.1, 0.01, 0.001, all that, you would see that this right here is approximately 0.69. This part right here. It does approach a number, and it's approximately 0.069. You can do the same thing for 3 to the x. F of x equals 3 to the x, and what you'd get for the derivative is 3 to the x times limit as h approaches 0 of 3 to the h minus 1 over h. I'm just letting the a here be 3 instead of 2, or a. Well, it'd be nice if that was the same, but it's a little different number. It turns out it's about 0.110. So this number does change, but it is a number. And I'll get more back to that here in a second. After we talk about logarithms. Yeah. The moral of this for now is that the derivative of 2 to the x, where the variable is in the exponent, it's that very same thing times a constant. Whatever the constant is, and we'll get to what it is more in just a second, but it's the exponential expression times a constant. Okay. Let's talk about e. The base e. The number e, the base e. Well, by definition, they let e be the number. E is the number for which the limit as h approaches 0 of a to the h minus 1 over h. E is the number for which that equals 1. that's how E is defined. You may have seen E different things, but E is the number for which that limit that we had, this, we got 2 and 3 as the base there, but E is that number for which that's equal to 1. What does that mean? Well, that means if your function is f of x equals e to the x, f prime then, being an exponential, it's e to the x times the limit h approaches 0 of e to the h minus 1 over h. Well, we said this for e is 1. So what's the derivative? Turns out the derivative of e to the x is e to the x. Kind of an unusual derivative. We haven't seen that before. Have we had a function where the derivative was itself? Other than 0, I guess. But a non-zero function, we haven't had one of those because we always did our power rule or product rule. But for e to the x, the derivative is just e to the x. It's its own derivative. Kind of an interesting thing. All right. Now, we usually think of e in terms of a number, and e is it is an actual number, isn't it? It's kind of like pi. Pi is 3.1415, blah, blah, blah. E is, does anybody know it? E is 2.718. Better. 1828 and then 1828, but then it's something else. Yeah. Yeah, it's not a rational number. It doesn't repeat a pattern. It keeps going and going and going. But that's the number, that's the base for which the derivative to that x power is itself. Kind of a nice little derivative. No work involved. Of course, there's always wrenches and loopholes that you have to go through. But if it's just e to the x, the derivative is e to the x. Okay. All right. And e to the x will come up a lot, as we'll see. So if I've got x squared, f of x equals x cubed e to the x, that was my function. What's the derivative? Well, it's a product rule, but first times derivative of e to the x, plus the second e to the x times the derivative of the first, that's 3x squared. So you get x cubed, 3 to the x, e to the x minus, plus 3x squared e to the x. Okay? So if you're doing the derivative just e to the x, it's e to the x. Now, what of course will happen? What if I have e to the 5x squared? Well, that's not just 5x, e to the 5x squared, is it? Because what's come into play here? Chain rule? Yeah, you got to factor in the chain rule. Yeah, just the e to the power, the derivative of it is e to the power, e to the 5x squared. However, what do I have to multiply by? The derivative of the 5x squared. The power itself, which is 10x. So it's going to be e to the 5x squared times 10x. Because it's like the power chain rule. It's not probably as clear as some chain rules maybe, because you maybe not see the inside and outside, but I've got, it's basically the e to the power is the outside and the inside is your power. So this is the derivative of the outside. E to a power is just e to a power. However, you have to do the derivative of the inside, which is 5x squared. It's the chain rule. With me? Okay. All right. So that's the thing. Yeah, if you got a power other than just x, you got to multiply by the also by the derivative of that power. All right, so let's say we've got y equals e to the minus u over e to the u plus 1. What's the derivative? Well, first of all, what should I use there? What rule? Quotient. Yeah, I got to use a little quotient rule here. Low, d high. Well, it's almost e to just a power, but it's e to the minus u. So that's going to be, do you see, e to the minus u, the derivative is going to be e to the minus u, but times negative 1. Times negative 1. Yeah, we are doing the derivative with respect to u since that's our variable. With me there? You have to do e to the minus u times negative 1. Because e to the minus u, it is e to a power, so it's just e to that power is part of the derivative, but then we have to do why the minus 1? Because you do the derivative of minus u. All right, then we've got what? See, that's low d high minus high, e to the minus u, times the derivative of the low. What's the derivative of the low here? Just e to the u. Because e to the u, the derivative is e to the u. 1, the derivative is 0. And then over low squared. Okay, now, all right, some nice things happen. So this will be e to the u plus 1 times be negative e to the minus u. Okay, here's what nice happens. E to the minus u times e to the u. What happens? That's 1. Yeah, they cancel. Different ways you can see it. This, again, is just, you can do it that way. You add the powers, right? E to the minus u plus u is e to the 0. That's one way you can see it. Or you can say, well, that's 1 over e to the u times e to the u. It's probably the easiest way to see it. Those just cancel. It's just 1. All right, so then we've got y prime. Now if I distribute here, well, minus e to the minus u times e to the u, that's minus 1. Same thing. Then we have minus e to the minus u, minus 1. I guess the thing about these problems here, they tend to get a little complicated, and simplifying is kind of half the battle here. But I'm seeing it's minus 2 minus e to the minus u over e to the u plus 1 squared. Okay. Questions? Why am I not putting in du dy? Yeah, here, because the variable, we don't have x's, we have u's, we are integrating with respect to u, because that's our variable. And so, I mean, if you want to think about it, I am doing, it's the derivative, the other part would be the derivative of u with respect to u. I'm doing the derivative with respect to u. So that's just essentially 1. So that's why I don't have the d to u. Is that what you're asking? Okay. All right. Yeah, I think I see. And the other thing is, it is, I know what you're asking now. The du, that can be confused with the u substitution stuff. Du dx, du equals dx. Yeah, in this case, we're not using the u substitution stuff. All right. Straightforward derivative. Okay. Well, the good thing about e to the x being its own derivative is when I go to the integral of e to the x dx, what do you got there? E to the x, okay? Yeah, if it's its own derivative, then the antiderivative is e to the x plus c. Now, the thing you have to watch out for is when you get e to something other than just x, e to the 2x, let's say. This is where, yes, we do have to use, we'll do this, a lot. So I just like to refer to it as a little simple u substitution, okay? Which, I guess if you don't see it, it's not so simple, but it is just a simple little u substitution because to get this to work, I just need this to be e to a power, which I'm going to let u be the 2x. See that? You with me there? And this, I call this simple because what does it turn out to be? Well, du is then 2 dx, right? The derivative of 2x is 2. And so du over 2 is my dx. So yeah, this is just going to work out to be e to the u times du over 2, or 1/2 e to the u du. So that's 1/2. Well, e to the u, the antiderivative of that is e to the u plus c. So I have 1/2 e to the u plus c. Just go back to then what u is, 2x. So when I say simple substitution, what I guess I'm basically meaning is you wind up with that little fraction because of the number there. But anyway. All right. What about this one? The integral of x squared e to the x cubed dx. Well, again, I need something there to work out because on the integrals, I don't have a product rule. Product rule is we're only talking about that for derivatives. This is integrals. Integrals, we don't have a product rule. And that's one thing we don't get to a lot in Calculus 1. But in Calculus 2, you have to come to realize that. In integrals, we don't have a product rule. So when I got a product that I want to do the integral of, I got to do something. Either use substitution or some of the other things we'll talk about when I'm doing an integral. Okay, so the only thing we know right now is use substitution. So that's probably where we should go. Try a little u substitution. What do you think we might get the u to be? Probably the power, the x cubed. U is going to be the x cubed, the power of the e. So that would make then du be 3x squared dx, because I do the derivative of x cubed, 3x squared and dx. And what I like to do is go ahead and divide off the 3x squared. That's my dx. Okay? So make that substitution. U is x cubed, so that would be e to the u. Dx then is du over 3x squared. And this works out very nicely with u substitution, doesn't it? Because we get rid of the x squared, don't we? So now we just have the integral of, voila, well, it'd be 1/3, wouldn't it? 1/3 e to the u du. Which is something we can do the antiderivative of. The antiderivative of e to the u is e to the u. So 1/3 e to the u plus c. Just have to go back in terms of x, so it'd be 1/3 e to the 3x squared plus c. Okay.